Good afternoon, everyone, and welcome to the third in our February 2016 series of webinars related to nuclear waste. This afternoon's session is on radioactive roads, transportation of high-level nuclear fuel waste in Canada. And this session, our sessions frequently have an expert presenter or technical presenter. This session is one of the exceptions to that. This is not a expert or technical presentation. It's an overview and an introductory discussion of radioactive waste transportation issues in Canada. And we have lots of material to cover, and we have lots of work to do in this area. And it's great to see so many joining the session and joining in on this important conversation. So we're going to start, just as we always do, with the basics, a quick background context setting for this conversation. And then we're going to focus in today on the transportation of high-level nuclear fuel waste, and particularly focused in Canada, although we certainly borrow some analysis from other jurisdictions. We're going to talk about NWMO's plans, their reference plans, talk about some of the risks related to the transportation of radioactive waste, take a quick and very initial look at transportation routes, possible routes, and identify a couple of related issues. Then a first conversation about next steps. So nuclear waste, radioactive waste are generated at each stage of the nuclear fuel chain, from low-level waste in the several first links in the chain, uranium mining, refining, processing, fuel fabrication, to production of low, intermediate, and high-level waste at the reactor, in the reactor during electricity production. And then high-level waste is our long-lasting legacy from that fleeting benefit of electricity production. The high-level waste is the irradiated uranium fuel bundle. So it goes in as uranium and it comes out as high-level waste, nuclear fuel waste or spent fuel. And that happens because the uranium in the reactor core is bombarded with neutrons. It splits, fissioning takes place. As a product of this chain reaction in the reactor core, which is kickstarted for the purpose of generating heat to produce the electricity, it generates a couple of hundred different radioactive waste products. And therein lies the problem. Many of these products, many of these radioactive isotopes or waste products are lethal, are hazardous for very, very long periods of time. Some of them very short periods of time, but many of them have a half-life of thousands, tens of thousands, even millions of years. And a half-life is the amount of time that is required to reduce the radioactivity by 50%. Generally speaking, 10 half-lives to stable. So if you have a material like plutonium, a half-life of 24,000 years, 10 half-lives, 10 times around the circle for half-life, and you've got 250,000 years of a material that has to be safeguarded, isolated from the environment. Even low levels of exposure to these materials, to ionizing radiation, can be harmful. And the wastes have to be isolated from the environment, from people, from plants, from animals, virtually into perpetuity. So to date, the nuclear power industry in Canada has produced 3 million bundles, about 50,000 tons. Newest number, I think, is 52,000 tons produced to date of this high-level nuclear fuel waste, irradiated fuel. And that volume is expected to double over the next 30 years. The industry has had an intention since the 1970s to bury the waste in a rock formation. The 70s, 80s, and 90s, it was the Canadian Shield. Through, as of 2005, Canadian Shield or sedimentary rocks of southwestern Ontario. And that intention to bury the fuel necessitates the fuel being transferred transported from its current location to any eventual centralized site. The nuclear industry in Canada is organized as the Nuclear Waste Management Organization for the purpose of developing a facility for the long-term management of the irradiated fuel waste or high-level waste. So the Nuclear Waste Management Organization is made up of Ontario Power Generation, owns 90% of the fuel and has majority control of the Nuclear Waste Management Organization, Hydro-Quebec, and New Brunswick Power. Atomic Energy of Canada Limited also is a waste owner and makes some financial contribution to the Nuclear Waste Management Organization, given the waste that they hold at their 2 laboratories in Chalk River in Ontario and Pinawa in Manitoba. So the Nuclear Waste Management Organization, established in 2002 at the direction of a piece of federal legislation, and embarked on a siting process in 2010 to identify a, in quotation marks, willing and informed community to become the host for a deep geologic repository, a deep underground repository in which this 50 to 100,000 tons of highly radioactive waste would be placed. So there are 9 municipalities. At one point, we were up to 22 municipalities. As of 2015, the Nuclear Waste Management Organization continues to investigate 9 municipalities as possible burial locations for nuclear fuel waste. You might see on the screen a map that has those 9 municipalities identified. So it's the municipalities who expressed interest. But in Northern Ontario, there are 18 areas associated with those 9 municipalities. All of those areas are actually outside the municipal boundaries, and those are the areas that are actually under investigation. Depending on the stage, they're general potentially suitable areas or candidate areas, but those are the areas that are actually under investigation. For the 3 in northwest and southwestern Ontario, it is within the municipal boundaries that the NWMO has said they will investigate possible sites. So as part of the Nuclear Waste Management Organization plan, they have to transfer the waste. The waste would be shipped from the reactor stations, or in the case of ACL's 2 research laboratories, from those research laboratories in Chalk River and Pinawa, they must be shipped, then transported to the NWMO selected burial location. And that's where we're going to focus in our presentation today, is on that transportation of the high-level nuclear fuel waste, which would be required if the NWMO was ever to proceed and be approved and move to construction and operation of a deep geological repository. Some fairly large ifs there, but certainly possibilities that we can't afford to ignore. So the reference plan, the Nuclear Waste Management Organization has produced many documents focused on the transportation of high-level nuclear waste, the fuel waste. Initially, in what they called the study period from 2002 to 2005, they produced a small number of reports, and none of those reports actually discussed, acknowledged, evaluated exposure risk, dose to public or workers associated with the transfer of the transportation of the waste. More recently, they've produced a number of documents, and the more recent actually do discuss dose, and we'll be looking at them a little more closely. So these are the earlier documents you have on your screen, and they are conceptual design, lots of them focused on very general descriptions of transportation and on costing estimates. There was also an earlier report produced during the NWMO study period by the same utilities, Ontario Power Generation, Hydro-Quebec, New Brunswick Power, organized differently as the Can-Do Owners Group, that did their first study on, or first publicly available study on cost estimates. And it was interesting because it used as their reference a 1,000 kilometer distance from the reactor, from the fuel location to a proposed or assumed repository location, which gives, I think, some insight into the industry's basic assumptions around their siting exercise. More recently, the NWMO has produced a number of reports that focus on issues around dose, design, and so on. Some of them still in the glossy brochure messaging kind of category. Some of them actually beginning to do some of the technical or approaching technical assessments. And we're going to look more closely at them. And of course, the most recent is a large glossy brochure, which delivers their key messages around the transportation of the fuel waste. So they began back in 2005, even in their initial final study, which was the 2005 report that recommended what they call adaptive phase management, which has as its endpoint a deep geologic repository. Even in those initial studies, the 2005 report did not spend a lot of time and attention looking at transportation issues, but they began the messaging that has carried through, which is that materials have been transported around the world for 40 years, no accidents that have resulted in releases of significant amounts of radioactivity. So the messages are around success. They are the success stories. Those are the messages through the NWMO documents. Then vary a little bit. Sometimes it's 40 years, sometimes it's 50 years, sometimes it's no significant amounts, sometimes it's no amounts that can be attributed to the transportation. So some careful messaging, transportation experience, the messages carry through. These are 2010 backgrounders. We hear frequently from the NWMO about the 1 million packages of radioactive materials shipped each year. Most contain medical isotopes, single isotope, most of them very, very short half-lives. So not exactly a fair comparison to fuel waste, which has a very high hazard level and has a very, 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 very long hazard life. But the messaging continues in the 2015, in the 2010 backgrounders, messages around it's not been transported widely in Canada. In fact, there's been very little transportation of fuel waste in Canada. There has been transportation of fuel waste primarily for the purpose of transporting fuel waste from a reactor station to the research laboratory. For example, when Darlington was observing Boeing in the fuel elements, they shipped some of those fuel bundles off to Chalk River for investigation. So we've seen estimates of either averaging 5 or 3 to 5 shipments per year. But again, they're single shipments. They tend to be a single fuel bundle or even a single fuel element shipped for research purposes, or the volumes that were shipped to Pinawa for research purposes at the Underground Research Laboratory in the 1980s. So again, nothing comparable to the kind of volume and frequency of shipments that we would see if the NWMO was to move into operation mode at a deep geologic repository. So one of the messages, of course, is that there's a strong international track record in transporting used fuel waste. 50 years, 20,000 shipments worldwide, and so on. And, key message is that we're to rely on that international experience. One of the challenges we have in Canada, not just in the discussion of fuel waste transportation, but more broadly, is that we have CANDU reactor design. 10% of the reactors in the world are CANDU designs, but we cannot necessarily rely on the analysis done in other jurisdictions of fuel waste transportation dose assessments, for example. So it's a bit of an additional challenge for us in Canada, because the messages from NWMO and the regulator are that we're to rely on this international experience. I just got a message that I lost voice. Is that the case? I think my mic is active again, so we'll continue. So we're told to rely on international experience, but we have a situation in Canada where we can't rely on international experience because we have a different fuel type. So that's a challenge we're going to touch on again a little later. So some of the materials that we're going to look at more closely now relate to the work done in the last few years by the Nuclear Waste Management Organization in developing their transportation options and assessment. So the NWMO now has a used fuel transportation package for people who are in the communities being investigated by the NWMO. You'll have seen the truck come to town a few times by now. So the NWMO has this used fuel transportation package. It is, in fact, a used fuel transportation package designed by Ontario Hydro in the 1980s, when Atomic Energy of Canada Limited was seeking approval for their deep geologic disposal concept, their idea of burying waste in the Canadian Shield. Ontario Hydro was basically their co-proponent and were responsible for transportation and siting. And Ontario Hydro, now Ontario Power Generation, developed a used fuel transportation package to put forward as part of that review. And in 2013, the Canadian Nuclear Safety Commission recertified that used fuel transportation package. So it was recertified without any opportunity for peer review, public review, or independent review. And we've not actually yet seen the documents related to that review. So this is what the NWMO version of that used fuel transportation package looks like when they're on the road. There is embedded in the middle of that long transport truck, which is actually a display booth and a display stand. There is actually a mock-up of the used fuel transportation package. The NWMO was saying in 2005, 2010, they were talking about transportation modes for used fuel would include road, rail, or water. More recently, they have focused on just road and rail and have not continued, at least in their documents, any discussion of the water option. And their basic assumption is that it will be a road transfer. And in fact, if the rail transfer includes road transfer. So for example, the fuel waste that would be coming from Bruce would go first by road to Godrich and move on to rail in Godrich, about 50 kilometers south, following down along the coast of Lake Huron. The fuel waste that would come from anywhere east, so Chalk River, Gentil, La Pro, would come by train to Mattawa and would come by truck to Mattawa and would be transferred to truck in Mattawa. So it would be first by road, then transferred in Mattawa, about 45 kilometers east of North Bay. So these are large parts of the project which have not been put really on the table by the NWMO, other than sort of as a fine print in one of their tables in their dose assessment reports. So their basic assumption is that it would be by road. And the numbers are fairly similar from 2005, 2010, 2015, in terms of the number, 622 shipments per year, 1 or 2 shipments per day. would be is a current estimate, and that would be for a 38-year period. That's the NWMO estimates at present. So they have the basics in terms of their reference plan, but it's very basic and it's very reference. The Nuclear Waste Management Organization and other nuclear proponents use this language of reference to say it's the plan in place for the present time. So they have reference case for the geological for the repository design, and they have reference plans for the transportation of the waste. And basically, it's a plan for the present time. So the risks associated. The NWMO has recently, in 2014, 2012 and 2014, done a series of reports specifically looking at dose assessment. And we're going to look more carefully at one of them than at the other two. But they did, in 2012, did a generic dose assessment for members of the public. So these are basically people along the transportation route, and concluded that there would be no significant effect. They also, in 2014, did a particular study on what's called the 9-meter drop test. So we've heard already that we'll be relying on international standards, international tests. And one of those is a set of tests. These are the safety tests that were referred to, are the tests as set out by the International Atomic Energy Agency. And the tests include a drop test. There's a set of tests for what's called normal conditions and another set of tests for accident conditions. And the test for accident conditions, so this is the toughest test going for the drop test, is a 9-meter drop onto an unyielding surface. So perhaps as a result of people making some jokes, perhaps about the 9-meter drop test, the NWMO has come out with a special report on why the 9-meter drop test demonstrates equivalency to an actual real-life accident scenario. I would refer you to the report, but I, for one, found it unconvincing. The other report, and we'll spend a little bit more time on this, is the NWMO report on transportation worker dose assessment. And so the NWMO has released in 2014 a report of about 100 pages looking at worker doses. So these are they focus particularly on the driver dose, but also did some for auxiliary workers. So in this, they have a number of different assumptions that they worked from. So one of their assumptions was that the irradiated fuel had been out of the reactor for 30 years. They assumed that, and I just we're going to use as an example the driver with a 600-kilometer range trip. So 620 shipments of the year, there would be a limit of 86 trips for the 600-kilometer distance, or 45 trips for the 1,200-kilometer distance. We're going to come back and look at these a little more closely. They estimated dose only for the outbound trip. So this assumes that the rig is clean, that there is no residual or lingering effect on the return trip. Assumes normal conditions, so no accidents, no accident scenarios were considered in the worker dose assessment. It assumed an average burn up of 220 megawatts an hour per kilogram uranium. And we'll talk a little bit more about that. They assumed the driver was 8 meters from the fuel package. They made certain assumptions around distance, speed, rest stops, assumed that overnight stops would be spent outside the truck. And this is even for the longer trips of more, I think 1,900 kilometer was the number used. They considered only gamma radiation. So they assume that the used fuel package is absolutely clean, that there's no surface contamination, and in particular, no alpha contamination. They assume a 40-hour work week, which it's a unique trucker who works a 40-hour work week, but they assumed a 40-hour work week, and they used a representative model of the package, and they used the 2003 Monte Carlo computer code from Los Alamos Nuclear Laboratory. So those are all their assumptions that they used to arrive at their conclusion. So their dose rates, they had a number, so they have included in their report, they do provide their dose assumptions at different distances from the used fuel package. They have calculations for exposure times for different tasks within the trip completion. And they have driver dose summaries. And in the middle column within this, we see that the driver dose summary for per shipment is 0.0040, and their annual dose is 0.34. This is megawatt. This is millisieverts per hour. So just to take a moment and check those assumptions, and because this isn't an expert or technical presentation, and because we don't actually have an expert on hand who has to date been able to evaluate these reports, and that is one of the things that we'll come back to in next steps, and some of the needs that we have in terms of evaluating and peer reviewing some of these key materials. But just to check some of the assumptions. So the NWM was made. We can't do anything about the assumptions that they have built into the model. So they're using the Monte Carlo code. It's a couple of decades old, and we have the same challenges in that from a public interest perspective, as we do with any of these conclusions arrived at by the nuclear industry proponents when they base their findings on computer modeling. So first of all, you don't know the data, you don't know the models, you don't know the codes, and you're not the person running the model. So we can't do anything about that, but we can look at a couple of the more obvious assumptions, or less black box assumptions that they have made. So NWMO uses a burn up. They took an average of the fuels from the OPG reactors and arrived at 220 megawatt hours per kilogram of uranium. They also have a 280 number, which is the 95th and 99th percentile. If you substituted the 280 for the 220, you would have an approximately 65% higher dose. So I think there are questions around the assumptions when we've averaged the fuel and we're making an assumption that the fuel has all been out of reactor for 30 years. We've got a number of assumptions there, which could be pretty significant variables. The NWMO has also assumed that it's an 8-meter distance between the driver and the fuel package. So a 25% reduction in that difference would result a 2-meter reduction, a 25% reduction in the distance would, by my very layperson calculations, result in a 75% increase in dose. The NWMO also assumes a 40-hour work week, taking just a 600K trip, 600-kilometer trip, which their scenario was that's from Darlington to Elliott Lake. So presumably they mean one of the candidate areas north and west, or north and east of Elliott Lake, but they said Elliott Lake, so 600 kilometers. They calculated 11 hours, and they said a 40-hour work week. Well, if you went to a 44-hour week, you could increase your trips from 86 to 100. If you went to a 60-hour week, you could increase your trips to 125, which would be approximately a 50% increase in dose. So when you add those increases, you come considerably closer to the 1 millisievert limit, which is the regulator's limit on public dose, on dose for a member of the public. So if we were to reach that, they would be out of, out of compliance with what is, by our understanding, already a quite permissive standard. 1 millisievert is the public dose limit, but it's generally accepted or generally assessed in the public interest community as being a quite permissive one. So not to come to any conclusions, but just to say, when we look at, when we look a little closer at the NWMO materials, we can see that there are a number of assumptions that have been made, which even from a non-technical perspective, we need to question. And I think if and when we get a technical review, we may have some additional assumptions that need to be really investigated. So looking at some of the non-NWMO material, and I've relied, there are a number of pieces of number of reports, pieces of literature that are available that are helpful. I've, for the purpose of today's discussion, pulled out only 3 of them. And the one that I actually find the most helpful is the radiation exposures piece done by the state of Nevada, Robert Halstead for the state of Nevada a number of years ago. And in fact, I'm going to rely on our summary of what's in the literature with respect to radioactive risks associated with nuclear waste transfer. I've also relied on Large Associates, a report done about 10 years ago, and the National Academy of Sciences has a report called Going the Distance, Safe Transport of Spent Nuclear Fuel. And we're going to just talk a little bit about some of the conclusions or some of the findings of these different reports. So National Academy of Sciences, I think, walks the line between the proponent's message of international track record, million shipments, normalizing this idea of transporting high-level nuclear fuel waste. They kind of walk the line between that and some of the more critical literature. And they say there's no fundamental technical barriers to the safe transport of spent fuel, high-level radioactive waste in the United States. When conducted in strict adherence to existing regulations, such transport is low radiological risk activity with manageable safety, health, and environmental consequences. However, there are a number of social and institutional challenges to the successful implementation. That success is based on several factors. This is according to the National Academy of Sciences report, including rigorous international standards and regulations, full-scale crash testing of transport packages, and a series of increasingly sophisticated analytical computer modeling. So we might want to pause and just ask if those factors are being met. So rigorous international standards and regulations. Well, we've already looked briefly at the International Atomic Energy Agency's standards, and I think that rigorous is not a word that I think most of us would apply to those tests. We also have an example, very recently, a Canadian example of a container having a package, a used fuel package, also for high-level waste, having gone through a certification process and having received certification from the Canadian Nuclear Safety Commission, and that is for the NAC package for the highly enriched uranium, the liquid uranium to be transported, or which is proposed for transportation from Chalk River to Savannah River. So this was a review process. We were given a limited opportunity to comment on the packaging. The Canadian Nuclear Safety Commission did allow public comment. Unfortunately, the changes to the package design were excluded from the information being made available to the public for purpose of comment due to competitive interests, copyright, patent interests. Nevertheless, that container was certified, so found by the Canadian Nuclear Safety Commission to be have met that rigorous standard. In October of this year, at the Chalk River Laboratory, the same cask was being used for its earlier purpose, its general purpose, that being solid fuel waste. And that cask was being loaded in the fuel bay at the Chalk River facility when it lost the lower bottom to the container. It dropped into the fuel bay. And there was some investigation of this. It was a protracted period before the Canadian Nuclear Safety Commission was actually notified of it, but through a posting on the Nuclear Regulatory Commission registry, we became aware of this. And in fact, the bottom of the canister had dropped because the conclusions of the manufacturer were because there were unqualified welders had improperly welded the seals, and so the canister had in fact failed. So there's an example of that rigorous international standard, rigorous regulation, rigorous certification process. We also have a used fuel transportation package now certified for use in Canada that was designed in the 1980s and has never been subject to any public review since that time. Full-scale crash testing of transportation packages under severe accident conditions is the other factor that the National Academy of Sciences says must be in place. In Canada, in the case of the NWMO packaging, there has been no full-scale. There's been scaled testing and primarily computer modeling. So we're relying on scaled tests and computer modeling. So for number 1 and number 2 of the NAS criteria, they haven't met. Number 3, a series of increasingly sophisticated analytical and computer modeling. Well, we're still relying on the NWMO is still using the Monte Carlo computer codes from 2003 from Los Alamos National Laboratory. So I don't know if that qualifies as an increasingly sophisticated analytical tool, but I would not think so. So the test requirements, this is the IEA. So we have rigorous international standards. I think I moved ahead of my slide here. So we have rigorous international standards. So we have the IEA test here set out. So the normal transport condition is a free drop test, dropped 1/3 of a meter, so 1 foot onto an unyielding surface. For accident conditions, that free drop test is dropped 9 meters onto an unyielding surface. And I'll tell you now, the joke I sometimes make about this is that when I'm sending Christmas packages by Bus Parcel Express, I think they could all meet the IAEA tests all meet the IEA drop tests. They also have a penetration test, a thermal test, and a water immersion test. So radiation exposures, I see that our time is moving along, so I had best do the same. So radiation exposures, there are 2 kinds of exposure. There's routine exposure, it's called normal exposure, and exposure as a result of accidents. So I'm going to borrow now from that summary produced by the state of Nevada, Robert Halstead from the state of Nevada, and our summary of that. So exposure due to transportation of fuel waste comes from routine, from accidents, or terrorist attack. Normal or routine conditions, the state of Nevada study showed that an individual who resides, works, or are confined 6 to 40 meters from the nuclear waste transportation route would receive yearly radiation doses equal to or in excess of the annual average annual background dose. So in Canada, that's 1.8 millisieverts an hour. So you're in effect doubling that dose. We can't do anything about background dose. So every additional dose is additive. The Sandquist report, which was referenced by the state of Nevada summary, talked about, also identified that depending on the number of truck shipments, maximally exposed individuals along highway routes could receive annual doses equivalent to between 2% and 266% of annual background. That's people who are co-users of the transportation route. Then releases due to accidents. Studies identified 3 different types of accident. The most severe accident identified that exposed individuals would receive a dose primarily from the inhalation, a dose of 10.2 rem, primarily from inhalation of radionuclides. And radionuclides released by accident would contaminate an area of approximately estimated 110 square kilometers. The state of Nevada noted that this was a conservative estimate, or an optimistic estimate, and this is one of the areas where we are most lacking in our Canadian review in terms of being able to evaluate effect. So routes, we are very early in looking at routes. We do have the 9 municipalities who have engaged, and in Northern Ontario, the 18 areas that are being investigated. So approximately 21 different potential locations. The NWO has provided distance and travel times, and they've identified their assumption that it would be most likely rail mode, but rail mode would also include a road option. We're going to look just at one area. So we chose Manitouwadge. It's sort of central to the different areas that are being investigated. And just taking a very quick look at what the NWMO has provided. So at the end of step 3 of the NWO 9-step process, it's divided into phase 1 and phase 2. At the end of phase 1, they identified the generally potential suitable areas. And so we're assuming that one of those, so this is the information that the NWMO provided. They simply identified where the national highway system is, secondary highways, and the route to Manitouwadge. No identification of the different general potentially suitable areas that I'll call candidate areas, although in the case of Manitouwadge, they are not yet. They have not yet released the phase 2 investigation that would identify candidate areas. So we're going to just use, for purpose of our very preliminary route identification, we're going to look at Manitouwadge, and we're going to look at the Black River or Bearhead Lake area just south of Manitouwadge, which the NWMO refers to as the South Central area. And here's what it looks like. Very preliminary map, but we have in the west small quantities, a small volume coming from Pinawa in Manitoba, the Underground Research Laboratory, and then we have a small volume coming from the Chalk River Laboratory, which is about center. Then we have from the Bruce, we'll look in more detail at a map that doesn't include Pinawa because it took detail away from us. So we have in the moving from west to east, we have Bruce, we have Pickering, we have Darlington, moving slightly north, the Chalk River Laboratory. Moving further east, we have Gentil at Bécancour in Quebec, and then we have Point La Croix in New Brunswick. So pretty significant distance, and also pretty significant that we see for both the Southern Ontario facilities, we have transportation up through the major transportation corridor. MapQuest likes to send the fuel waste through Toronto when it's coming from Pickering, and up Highway 12 when it's coming from Darlington. The NWMO, of course, hasn't identified any routes and may or may not disclose them. They have disclosed some of their thinking around the transportation routes. For one, they have disclosed that information about the routes will be made available only to security forces and only on an as-needed basis, meaning that the populations along the route will not be given any notice of the transportations. And they have also disclosed that municipalities will not be able to influence the route within their municipality. So, for example, they won't be able to direct the route. So they will potentially be able to restrict the use of municipal roads during the spring thaw on the basis of it being damaging to the road. So there could be a period of reprieve each spring during spring thaw to avoid the heavy weight impact on the road. Other than that, the municipality, according to the NWMO, has no jurisdiction, which I think is quite consistent with the previous presentations that we've had from the Canadian Environmental Law Association about the municipalities not having jurisdiction in nuclear matters, including and particularly this matter. So some of the related issues, I see we're at 12:53. I'm going well into our discussion period. Couple of related issues. One is, I've already mentioned, the proposal, the plan to ship highly enriched uranium, this is liquid uranium, from Chalk River to Savannah River in South Carolina. Another proposal is the proposal to bury so-called low and intermediate level radioactive waste at the Bruce Nuclear Generating Station on the shore of Lake Huron. This is a proposal, the March 1st deadline for the Minister of the Environment to release her decision statement on this proposed repository is coming up fast, less than 2 weeks away. And this really, Ontario Power Generation's deep geologic repository beneath the Bruce is, by our assessment, the poster child. It's the test run for gaining easier approvals for their intended deep geologic repository for nuclear fuel waste or high-level waste. So those are a couple of related issues. In terms of next steps, there is lots to do. Some of the big needs that we have, and I say we both organizationally as Northwatch, but I think as the community of concern who are tracking the radioactive waste burial exercise and the related transportation issues, we really need technical reviews of the NWMO transportation assessments. As concerned citizens and informed citizens, we're able to identify some of the gaps, inconsistencies, questionable assumptions, but we do need some technical reviews done to support our own evaluation. And we need route mapping and we need engagement along the routes. If you recall, those maps were going through along major transportation routes and through major communities along the way. And we really need to increase the engagement along those transportation routes. And most practically, we need to establish a nuclear waste transportation working group. And we are in the early stages of that in Northwatch, but would really welcome making that a broader effort with others on this call or others engaged in the issue. So that said, I'm going to shut the recording and we'll move to question and answer. So thank you.